think about the origin of scientific graphs, data visualization, our minds usually jump to the Enlightenment, maybe the scientific revolution. But the real story is so much more surprising. It starts with a 14th century bishop who was an advisor to a king.
Right now, if you want to understand any kind of change, whether it's in the market, in physics, or really any science, we all reach for a graph. We've got an x-axis, a y-axis. It's the basic language we use to talk about data. It feels so modern, right? Like it has to be a product of the last few hundred years.
But what if that entire visual language, the very idea of plotting a changing quality against a steady one, was actually born in the 1300s? What if it was invented by a philosopher who used this exact tool to challenge the physics of the ancient world and to debunk the king's own astrologers? How did he even come up with it, and why isn't his name more famous?
Today we're exploring the absolutely revolutionary work of Nicole Oresme. We'll be focusing on his key writings from around the 1350s and 60s. And as always, you can find the links to the full bibliography in the description below.
So who was this guy, Nicole Oresme? Well, he was anything but a simple scholar living in the so-called Dark Ages. This man was a genuine intellectual powerhouse, one of the most original and brilliant minds at the University of Paris, which at the time was the center of the intellectual world.
And his career path was, frankly, meteoric. He starts out as a theology student and then becomes the Grand Master of the incredibly prestigious College of Navarre. From there, he becomes a trusted advisor to the future King of France, Charles V, and eventually gets appointed bishop. So this is not some isolated academic. He's a man of real influence at the highest levels of both church and state.
And that just illustrates his incredible range. I mean, he was an economist who wrote one of the first ever books on monetary theory. He was a physicist who dared to question Aristotle, a translator, a brilliant mathematician, and a fierce opponent of court astrology. He was a true Renaissance man, a full century before we say the Renaissance even began.
But his single most important idea, the one that truly echoed through time, came from a really basic question. How can we actually represent something like the intensity of heat or the speed of an object using geometry? How do you literally draw a picture of change itself?
He came up with something he called the doctrine of the configuration of qualities. Okay, it's a bit of a mouthful, I know, but the idea behind it is just breathtakingly powerful. What Oresme did was create a visual language to make invisible concepts, like heat and, most importantly, velocity, totally visible and measurable.
Here's how he set it up. He imagined two dimensions. The first one he called longitude, or longitude. This represents the subject itself. So for motion, this was simply duration, time. The second he called latitude, or latitude. This represented the intensity of the quality at every single point. For motion, this was velocity. He basically invented the X and Y axis for plotting physical change. It's that fundamental.
And the process was just so elegant. Okay, first you draw a horizontal line, that's your time axis. Then at every single instant along that line, you draw a vertical line straight up. The height of that line represents the velocity at that specific moment. Then you just connect the tops of all those lines, and the shape you get, the configuration, is a literal picture of the motion. And the real genius part? He proved that the area of that shape equals the total distance the object traveled.
This simple system makes really complex ideas totally intuitive. So an object moving at a constant speed, well, that's just a rectangle. Its velocity, its height, is the same at every point in time. What about an object accelerating uniformly from a dead stop like something falling? That's a right triangle, with the velocity line steadily getting higher. This was a geometric proof of what became known as the Merton mean speed theorem, and it's a direct, undeniable precursor to the work of Galileo.
In his own words, quality is to be imagined to have two dimensions. Now for him, this wasn't just some clever analogy. He truly believed this was a real way to conceptualize and, more importantly, to quantify the physical world.
Oresme's incredible graphical thinking didn't just stop with motion. He also took his geometric reasoning and applied it to one of the thorniest problems in mathematics, not just in his day, but for centuries after, the concept of the infinite.
So let's look at the famous harmonic series. It looks pretty simple, right? You just keep adding smaller and smaller fractions. Since the pieces you're adding are getting closer and closer to zero, your intuition tells you that the sum should eventually level off at some specific number. This puzzle drove mathematicians crazy for centuries. Oresme was the first person we know of to prove, definitively, that it doesn't. It actually goes to infinity. And his proof is a masterclass in elegant thinking. He didn't need any complex calculus, just a really clever insight. He decided to group the terms together. He saw that 1/3 plus 1/4, well, that's bigger than 1/4 plus 1/4, which is 1/2. Then he took the next four terms, from 1/5 to 1/8, and saw that their sum was also bigger than 1/2. He realized you could keep creating these groups forever.
So the conclusion was just undeniable. If you keep adding a value that's more than 1/2 an infinite number of times, your total sum has to be infinite. It was just beautiful, simple logic. He had tamed an infinite puzzle. What's even more incredible is that he also used these geometric methods to prove the sums of certain series that do converge to a number, laying down the conceptual tracks for mathematics for centuries to come.
Now, it is really easy to look at a figure like Oresme and frame him as this lone scientist fighting against a superstitious church, but that completely misses the point of his motivation. We have to remember, this was a deeply devout man who would become a bishop.
You see, for Oresme, reason and science were not the enemies of faith, not at all. They were its greatest allies. He believed that God was a rational creator, which meant the world he created must also be rational and understandable. So for him, science was a tool to fight against what he saw as irrational and dangerous things, like magic and astrology.
And he really put this into practice as a royal advisor. He wrote entire books warning his patron, King Charles V, that astrology was a fraud. When people pointed to so-called marvels or magical events, he looked for the natural causes. He even used highly advanced math to argue that the orbits of the planets were probably incommensurable, meaning their patterns would never perfectly repeat, which made the specific predictions of astrology literally impossible. So what is the ultimate legacy of this 14th century genius? Well, his ideas definitely didn't just disappear. Instead, they echoed down through the centuries, and they laid an absolutely crucial foundation for the scientific revolution.
You can draw a straight line, no question, from Oresme's work to the giants who came after him. His graphical proofs of motion were picked up and expanded on by Galileo for his study of falling bodies. And his whole system of longitudo and latitudo is an unmistakable forerunner to the coordinate system of René Descartes. Oresme provided the very language, the geometric grammar, that they would later use to describe the universe.
So what are the big lessons we can take away from Oresme's work today? Well, there are three really powerful ones. First, the power of visualization. He proved that turning an abstract concept into a physical shape can show you truths you'd never see otherwise. Second, question the foundations. Even an authority as huge as Aristotle wasn't beyond questioning for Oresme. And third, be a champion for reason. Use it to find natural explanations and to push back against claims that have no evidence.
If there's just one thing to take away from all this, let it be this thought. We can call it the Oresme principle. Before you can calculate change, you must first picture it. That idea, that conceptual leap from just numbers to images, that's his legacy in a nutshell.
And that leaves us with a final thought for your own work. Oresme's incredible breakthrough came from looking at something everyone knew, motion, and representing it in a totally new way. So the question for us is, how am I visualizing our own data, our own problems in a completely new and different way? Reveal the groundbreaking insight that we've been searching for.
Disclaimer and bibliography in the description.